Hello, and thanks for coming. I'm doing my annual talk at SIGGRAPH about the state of development of VRay and some of our other upcoming products. So this is generally the overview for my talk. We'll go through some of the recent updates in VRay that we did for 3ds Max and Maya. Then a few words for VRay for Houdini and Cinema 4D. We'll spend some time on VRay GPU and what's new there. And then we'll talk a little bit about Project Lavina, which is our real-time ray tracer that we showed for the first time at SIGGRAPH last year. And finally, a few developments that are coming for the future. So first, this part is going to be a little bit technical, but I want to mention it a little bit more specifically because it's a major change in how VRay works and how VRay calculates render elements. And this took some people by surprise, so I wanted to spend a little bit of time to explain why we did this. There's a new option in VRay. If it's well hidden, so you won't usually find it, but it's called consistent render elements, which changes the way that VRay calculates lighting render elements like global illumination, direct lighting, specular, and reflection. And we did this change so that we can implement some optimizations in VRay, like the adaptive dome light, adaptive lights, and some other optimizations for the future. This is implemented both in the CPU and GPU, so they work identically. But basically, the idea is this: if you have a light source, this is a sphere light source, VRay basically calculates the effect of this light source on the camera ray. So the camera ray is this one here in white. And the effect of this light source on the camera ray can be calculated in two different ways. It can be done with a shadow ray, or it can be done with a GI ray in this case. And there's a formula that allows you to combine these two calculations to get the final result. And in older versions of VRay, we used to split the lighting and GI render elements based on these different types of rays, which led to this weird effect of the light source leaking a little bit into the GI render element. And this was, at some point, it was not really desirable. So we had to change this. So for the latest updates of VRay, what you will get is this result, where all of the lighting calculation, all of the lighting contribution will be stored in the lighting render element, and you only get GI in the GI render element. And this is how things should have been from the beginning. So what we did before was not exactly quite accurate. It was easy to do, so that's why we did it, but it caused us problems further down the road. So now we've taken the opportunity to fix this. And there is exactly the same situation with reflections and the specular render element. So in older versions of VRay, you could get the reflection of the light source here in the reflection render element, even though it's still the same effect. It's still the effect of calculating how this light source affects this camera ray. And in the new versions of VRay, all of this goes into the specular render element, and you only get reflections in the reflection render element. So for smaller light sources like rectangle lights and spherical lights, this is not really that obvious, and it doesn't bother people too much. The change is a little bit more drastic for dome lights, and we will probably need to tweak this a little bit to make it slightly more similar to what we did before. But I just wanted to make sure that you are aware of this change. So again, why we did it? It allows us to do some optimizations in VRay that were not possible before. Other things that we did in the recent updates is we improved the way that VRay handles many light sources. We had the adaptive lights before, and they work really well, but they require the light cache to work. And also, still the light cache could be on the slow side once you start to get thousands of lights. So we had to improve this, and for update to VRay Next in 3ds Max, and also in the latest update of Maya, we added an additional way to calculate the light sources if adaptive lights are not available. It's called Light Tree. It's enabled by default, and VRay uses it whenever it makes sense. And it speeds up a lot the calculation of scenes that either use brute force GI without the light cache, and or just speed up the calculation of the light cache itself. It's implemented for VRay CPU, it's implemented on the GPU, and it's also implemented in our real-time render, so you can render thousands of light sources with very minimal performance hit. I have a more in-depth talk about this at my Total Chaos talk, which you can check on our YouTube channel. We also improved the lens effects in VRay, and we also released the Nuke plugin that implements these lens effects. We had customers that wanted to be able to apply the lens effects in their compositing pipeline, so we just released the free Nuke plugin for that. And there's just a reminder that we also have a Nuke plugin for the VRay denoiser that you can also use in Nuke. Another new feature in the recent updates is the memory tracking feature, which tells you, which gives you a detailed report about the memory usage of different parts of the scene. So you can generate an HTML file or a JSON file that tells you how much memory is taken up by each object or by each bitmap texture, and it can be very helpful to figure out why the memory is, why the scene why a scene may use a lot of memory. It will be improved gradually over the next few releases. Right now you do get a nice split of most of the things, most of the memory that VRay allocates, but it will get even better in the future. Finally, we also did improvements to the light cache. It's one of the oldest things in VRay, oldest pieces of code in VRay that has not been changed, that hasn't changed too much over the years. But in the latest updates, we improved it by changing the way the samples are stored in memory. It basically allows us to reduce the flickering of the light cache animations quite a bit. So in the latest versions, they should be a lot better than it was before. Again, it's implemented for VRay CPU. It's the default for new scenes. It's implemented in VRay GPU, and we also use this in our real-time render because the algorithm actually allows very efficient real-time calculation. Other little improvements to VRay GPU: support for the AL surface material and support for the VRay distance texture. These were one of the most requested features for VRay GPU, so now they are in our official builds. Finally, next, VRay for Houdini is released since yesterday. So, yay. We announced the beta version at SIGGRAPH last year, and we were under the impression that we will be done with the release in a couple of months. So this ended up being closer to a year, but the delay was worth it because it allowed us to make VRay for Houdini more stable and more usable. So the first version is really good. We have already a couple of customers that have used it in production and seems to be fairly stable, works well. Supports a lot of the native Houdini workflows. We also developed some features in VRay specifically for Houdini so that you can do massive instancing. We also made it easy to exchange data with other VRay integrations, so you can take VRayScene files or VRayProxy files from 3ds Max, Maya, or something else, and load them up in Houdini and render them with VRay for Houdini. The first release is out there. Obviously, we'll continue improving this. If you want to give it a try, you're more than welcome. If you have any feedback, it's also very welcome. VRay for Cinema 4D is another integration that we're working on, and we are basically rewriting it from scratch. Why? Because we looked at the current state of VRay for Cinema 4D, and we realized that some important features that people wanted to use in their everyday workflows were not working very well. and unfortunately we couldn't just patch them up, so we had to start all over again. And we knew that things like interactive rendering, motion blur, GPU support, efficient texture mapping, handling would be important, so that's what we did right from the start. And the last point about texture mapping stuff is really specific to Cinema 4D, because it does texture projections a little bit differently from all the other integrations, all the other applications that V-Ray is integrated in, and it caused us a little bit of headache with the first, with the original version of V-Ray for Cinema 4D. So this time we wanted to do it right. So basic stuff is working. Export of geometry, IPR, basic lights, and we are working now on extending the support for materials, textures, and all the different light source types. And this is a short video to show you where we are at with V-Ray for Cinema 4D. The entire video is recorded with V-Ray GPU. So we're looking at a simple scene that our 3D guys did. It's lit by a V-Ray dome light. So we can change stuff, and then on the light you can change the colors and everything. It updates obviously as you would expect in any other V-Ray integration. Playing with the material on the head of the mechanical bead thing. So we can turning on reflections, refractions. Next we'll play with the material of the body of the beam. Doing some simple color adjustments, and then we're going to add a texture map for the reflections. It'll take a while to load the texture. This is just isolating the same texture. And playing with the tiling parameters of the texture map. And finally, we'll render the scene with the production render, which is also V-Ray GPU, but this time in bucket mode. We have all the various render settings of V-Ray just dumped here because the UI right now is generated automatically. But for the final release, we'll probably hide a lot of these because they are V-Ray is a lot simpler these days, so you don't actually need all of these controls. So this will get a lot simpler in the future. And we're done. So this is where we're at right now with Cinema 4D. Things will progress and we'll have more updates and hopefully a public release a little bit later in the year. Next topic is V-Ray GPU. We've been working on 3 major updates of V-Ray GPU over the last few months. The first is RTX support. based on Optix 7. This required major changes to VRay, but the results are worth it, and we expect a release later this year. We are also working on OSL support and out-of-core geometry rendering for VRay GPU, which would allow us rendering of more complex scenes. Other improvements to the displacement from VRay. This is already implemented in VRay GPU in our nightly builds, and it works fine. Also a popular request by a lot of customers. We are working on making VRay GPU faster, getting to the first pixel by optimizing the scene preparation phase, and we are also working on better support for NVLink. So I mentioned Optix 7. So what it is, first, it's a new API that NVIDIA officially announced yesterday. We've been working with NVIDIA on Optix support for VRay for a while now, but the initial version, Optix 6 and earlier, they did the job. They gave us a nice performance boost for VRay GPU, but we felt that the API was not exposing the GPU in the best possible way, so we thought that there should be a more efficient way to use the GPU. So we discussed this with NVIDIA at SIGGRAPH last year. It was a heated discussion, but they listened to our requests, and we got a new lower level API called Optix 7. We got the first, we worked with NVIDIA on the initial drafts of the API. We gave some input and feedback, and we got a working version of it sometime in April. So since then, we've been working on rewriting VRay GPU to use this new API. And what does it give us? First, the memory, the GPU memory management is a lot simpler for us and a lot closer to what we had before. Also, Optix is generally a runtime compiler, so it takes the GPU code for the specific scene that the user is rendering, and it compiles it for the GPU that will be doing the rendering. And this is done so that you get the maximum performance, but unfortunately it takes a little bit of time, and it's not a very trivial amount of time. You could be looking at half a minute, 1 minute of compilation before you see anything in the frame buffer. So we wanted more control over when and how this compilation happened. And especially in IPR, it could be really distracting if this recompilation happened when you started adding new shaders or new lights. So we wanted more control over that. Also, VRay GPU is distributing the work to the GPUs in the system for multiple CPU threads. We try to keep the GPU busy all the time. So with the previous versions of Optix, this was not really optimal, but Optix 7 allows us to do the same thing that we do for CUDA and keep the GPU at full load while VRay is rendering. So this gives us a nice performance improvement. Also, as you change geometry in the scene, when you start adding objects, moving objects, and so on, we have more control over how and when the geometry on the GPU is updated. The nice thing about Optix is that it handles all the geometry stuff internally, so we don't have to deal with this. But we wanted just a little bit more control over when exactly this happens. And because Optix takes care of all the geometry stuff for us, it turned out that some things are actually very easy for us to implement in Optix, like the 2D displacement was super easy to get working compared to our CUDA version. And we got the API, we did tests, and yes, it was worth waiting for this new API because it gave us a nice speed boost compared to what we had with previous versions of Optix. And in our tests, the Optix 7 version of VRay GPU is always faster than the CUDA version. The speed up depends a lot on the scene and the complexity of the shaders. Heavier scenes with more instances are faster. If the materials are complex, then the Optix doesn't unfortunately help that much because only the intersection of rays with the scene is hardware accelerated, but still it's faster than our CUDA version. We need one little final feature for our Optix integration to be fully complete, which will allow us to do ambient occlusion and rounded corners with Optix. And here at the end, I would really like to thank NVIDIA for helping us with Optix. There were a lot of things that we didn't know about the API. They gave us examples, helped us track problems in our code. So things that were really, really helpful. On this slide, some performance comparisons between our CUDA version of the code and the Optix version of the code. As I told you, if you have simple shaders, you get more speed up. If you have more complex shaders, it's not that big, but still faster than our CUDA version. This is one Evermotion scene that I rendered. It has a few hundred light sources. Here, our new light tree implementation helped a lot, but it renders fine with Optix 7, and it's it was really cool to see this result. So several benchmarks on a few different scenes. The orange bars are our CUDA version, which is the current version of your GPU. The green bars are the Optix 7 version, and Optix 7 is always faster, sometimes a lot faster. This scene here, where you get this huge speed up, it contains a lot of proxies and a lot of instances, and this is where Optix really, really helps. The other development that we're doing for VRayGPU is support for OSL, the open shading language, which is becoming more popular now that it's integrated natively in 3ds Max. We did try to support OSL a while back in 2015, but it was a little bit too early. We got to some point, but we had to give up. But in the recent months, NVIDIA started contributing to the OSL project, and most of the problems that we had initially were resolved, so we were able to continue our work, and we already have OSL working in our internal builds. At this point, only for textures or patterns, not for closures yet, although they would be easy to do because we already support GLSL and MDL in VRayGPU, and they have closures, so we can just reuse that code. So the rendering is fine, it works, but before you get to the rendering point, there's a certain amount of time that you need, that VRay needs to compile the shaders, the OSL shaders for the GPU, and this part specifically needs some improvement. These are the three materials for the picture on the previous slide. This is just a larger resolution version, and this is a short video to show you how this was set up. So basically, all the textures in this scene are OSL nodes. In this case, we are using the VRay OSL texture, but this works fine with the 3ds Max version of the OSL map. So at this point, we're just wiring up together all the shaders. So I'm not gonna wait for all that. We'll render this scene twice, once with VRayGPU and once with VRay CPU, and we'll compare the results. So once you start rendering, there is this shader compilation phase that takes a while, like I told you before. So unfortunately, as you have more shaders in the scene, it takes more and more time to complete this phase. But when it's done, you get a render, which in this case is not impressively fast because it's running on a GTX 650, but it still runs fine. So this is the CPU version, and then we'll render it with V-Ray GPU. Sorry, the CPU version of V-Ray. Render, and finally we'll compare the two results, which in this case surprisingly look exactly the same. But that's the goal of OSL, right? If you have the code, it should run exactly the same anywhere. CPU, GPU, it shouldn't matter. So you should get the exact same result. And it works in this case. Some other examples of shaders. This one is a interesting little shader called interior box mapping. It's helpful if you need to model a building, but you don't have time to model the interior of the building, and you just want to show some kind of dummy geometry inside, like rooms through windows. So the only geometry in this scene is a single plane, to which we assign an OSL shader, this interior box mapping shader. And after the said shader compilation phase is done, you get this result. And the cool thing is that you can change the viewpoint, and it simulates like an interior, very simple interior scene. It's a cool little trick if you have to do an entire building. All right, so the next thing that we're doing, the next major development for V-Ray GPU is out-of-core rendering. We've had on-demand texture loading for V-Ray GPU for a long time. It works really well to reduce memory usage for large scenes, but it only worked for textures. Geometry is a little bit more complicated. For textures, there are mip-map levels, and we can only load the level of detail that's needed for the scene. For geometry, there is no such thing, so you have to handle the geometry at its original detail. And implementing this in V-Ray GPU requires major changes to the render. The overall approach is not that complicated. You just split up the scene in little boxes or voxels that contain pieces of geometry, and then we can upload only parts of these, only a certain amount of these voxels to the GPU. We can intersect the rays that we have currently with what's on the GPU already, and if something else is needed, if there's a piece of geometry that is needed to intersect with some ray, we can record this and then upload it to the GPU and repeat the whole process until we are done with the intersection of all the rays. And this works, and of course the trick is making it as efficient as possible. And the image on the right there is 3 Lucy statues, which are copies, they're not instances. So you get a total of 84 million triangles, which we rendered with only 2 gigabytes of GPU. Gosh, they actually rendered on this laptop, which was really cool. This is another scene that our 3D guys prepared. It's a little bit more complicated. The actual scene required more than 20 gigabytes of GPU memory to render on an RTX 8000 card. But if we use the out-of-core version of V-Ray, we can limit the geometry cache to just 2 gigabytes, and in that case, we were able to render the scene on a regular RTX 2080 Ti. Obviously, it took a little bit longer, but it still rendered. I also did a few tests with the Lucy scene from the previous slide to try and see how the amount of memory affects performance. It's not terribly bad. I thought the results would be much worse, but we still have work to do to make this line more So, and here we have a big task ahead of us because we're working on 3 things in parallel. And at some point we'll have to merge the code together. And it will be a bit of a challenge. But hopefully everything will be okay in the end. And finally, when we are done, we have to make sure that everything works both with RTX and CUDA. All right, so that's it about V-Ray itself. The next topic is about Project Lavina, which is our real-time ray tracer based on DXR, which is DirectX with an extension for ray tracing. DXR was announced at GTC last year, and we decided to see how fast it is and what we can do with it. So the result is this real-time ray tracer that we've been working on. We showed a very, very early prototype last year, but since then a lot of things have actually changed. Now we also can do simple manipulations of the scene in Lavina. You can select and move objects and lights. You can import other objects like VRayScene files or VRayMesh files. We support procedural textures, so not only bitmaps, but also simple noises, color corrections. The lighting system is improved. We have important sampling for the environment to get image-based lighting, different types of lights. We added the light tree implementation from V-Ray to support multiple light sources efficiently, and also the hash map based light cache for efficient global illumination. We've improved also our denoiser so that we can handle reflections and refractions a lot better than we did before. And finally, we also added multi-GPU support, because once we added all those features, things kind of started being a little bit slower. So we support multiple GPUs now as well. Here's a video of me playing with various scenes here. You can see all of these scenes at the show floor. We have a pod at the NVIDIA booth. NVIDIA was very gracious to allow us to use a couple of machines at their booth. So you can see all of this working in real time there, and you can play with it. So all the assets and animations here were done in other DCCs like 3ds Max and Maya, and then the VRayScene file is exported and then imported into Lavina, and you get all the materials, the animations, the light source, and everything. This scene here is interesting because it's from a project that we did a few years ago with Kevin Margot, who was then at Blur. And he had this idea of a short film to do, and he wanted to explore virtual production. Back then we needed, I think it was 4 VCA machines to render this in real time. And now we can do it on one RTX card, which is kind of amazing. All right. Like I said, Project Lavina is at the show floor. Go and play with it. It looks really cool. Other things that we are working on: a material library for V-Ray, specifically in V-Ray for 3ds Max and Maya. We've had a material library in V-Ray for SketchUp and Rhino for a long time, but nothing that you could use in 3ds Max right away. But this is coming, and is also we provide a few hundred materials, but you can also add your own to the library if you want to. It has a nice browser with all the thumbnails and everything. You can search for specific materials. Works really well. And to go with this, we also added a custom preview scene to the material editor in 3ds Max. So you can replace the default sphere with something more complicated if you want. And we actually went a step further, that everything that you see in one material swatch is actually a VRayScene file that you can also put any VRayScene file there. It can contain any light sources, any objects. well, of course, you also have to keep in mind that the more stuff you add, the slower it will render, but you can get a good preview of, much better preview of the materials. There is also a new frame buffer that we are working on. We showed a concept of a new frame buffer maybe 2 years ago, but we had to stop the development for a little bit because we had to work on other things. We are now getting back to this, and one of the two main features that we want to add in there are basic compositing capabilities, so you'll be able to get your render elements and actually do your compositing inside the frame buffer itself. And as part of that, we'll also be adding a light mix type thing, so that you can control, if you have light select elements in the scene, you can combine them in the final image and adjust the intensity of the various light sources right inside the frame buffer. I don't have an image for this, mostly because the UI is not final and I don't want you to see developer stuff, but it's there, it's working, so we'll get to that. Other things that we kind of had to work on, we noticed somewhat unhappily that scenes are getting more and more complicated these days. People just add tons of proxies to their scenes, also VRayScene files, and in this case the viewport performance of the VRayProxy could become a bottleneck. So we are specifically working to optimize this, both in 3ds Max and Maya. And we also had to do specific work on making the Alembic reader a lot faster than it is now. We actually found a few inefficiencies in the Alembic library itself. So we've submitted a couple of fixes to the official GitHub repository. One was accepted. I hope that the other one will be accepted too. But when this is combined with our own internal optimizations, for some Alembic files, we get up to twice the speed for loading the files before rendering. So it's a nice speed improvement. Also, we're looking at how we can use USD Material X with V-Ray. There are a bunch of talks at SIGGRAPH this year about both Material X and USD, and we're trying to figure out where V-Ray fits in all that. We have a couple of ideas, so we'll see. And in addition to the viewports, we're also working on making the proxies render faster. Not only proxies, just any types of instances. So this will be not only for proxies, but for things like force pack. To do this, we've updated to a new version of the Embry library, Embry 3. It has some specific optimizations for this case, for proxies and for instances. So we hope to be able to use these. But it requires some work on our side. And I think that's all from me for today. So time for questions.